Good evening, everyone. My name is Vanshi Sethi, and I'm a third year student of IIT Guwahati. And today I'm here to present my internship 3, that is for DA 379, and its topic is post-stroke gait analysis based on the kinematics data and interpretability using explainable AI techniques. So firstly, let's understand the problem that why gait analysis is needed after stroke. When a person suffers from stroke, if they are a survivor, generally there's a lot of abnormality in the walking pattern of a person that is generally due to the problems with the brain connections like that. The signals are not getting properly to the muscles and we are having a stiff kind of movement or not able to lift the legs properly and we are scratching on the floors like that. This thing happens with a lot of patients that they have some kind of difficulty in their walking. It could be like they are totally dependent on another person to move from one place to another, or there could be mild abnormality which they can support on their own. But in order to analyze all these things so that it can be easily used by the scientists or doctors, we need to analyze this problem. And for this problem, we can use different kinds of data. The data could be kinetics. Kinetics is using of ground reaction forces. Okay. Then we have kinematics. In the kinematics part, there is angle. We will look at the angles in 3 dimension for all the parts of body that we want to include in our gait analysis. It's generally the lower body, like the angles of knee, hip, pelvis, ankle, all these things. And also we have spatio-temporal way. In this thing, what we do is we are able to see the whole trajectory. Means the swing phase and the stance phase of a person, and also how much width is there between their legs or how much they are taking in one step or the stride length like that. We analyze all these things and speed also. That is how we are able to differentiate a healthy person with a stroke person. Apart from that, EMG signals is generally used in all the previous researches that I studied. But one of the major limitation of using those EMG signals is that we really need to install a lot of sensors. We need to do all the clinical analysis. We need to gather so many people for that and then use it. Then it becomes a lot more easier. Otherwise, the data that is regarding EMG, which is available online, it is generally in the form of, time series. We can't use a time series in case of EMG. EMG is a continuous signal. So we need the raw data and that is mostly not available and we need to do experiments in lab. So that thing was not available. Then one thing came in my mind that alone with only the kinematics data, can I do this research? So yes, that is what we'll be doing in this part. So what solution we built? So we firstly took this band cricking data set, which consisted of 138 healthy people and 50 stroke patients. So it had a lot of data. There was some EMG data, which was not useful. Apart from that, COM data, center of mass, GRFs, they were also given. And apart from that, 4 angles were given: ankle, knee, hip, and pelvis for both the stroke patients and the healthy patient. We use this data only, these 4 columns. So what we did is we converted them into entropies. There were 4 entropies. One was a sample entropy, approximate entropy. Then we had fuzzy entropy because sometimes things don't actually match exactly. So fuzzy thing is always needed in this field of machine learning. Then the last thing was spectral entropy. Yes, spectral entropy is when we converted all this time series into frequencies. Then we were able to derive those things. Then we did the class balancing. We took 50 healthy and 50 stroke patients in order to balance out the class so that there's no biasness towards the healthy part only. So then we did the MRMR. MRMR is the maximum relevancy, minimum redundancy. That is, we choose the most relevant features, but minimum redundancy means we don't want two similar features to be selected. They should be like, in PCA, we have studied two almost distinct things are selected 90-degree to each other like that. Then we have the model training. We trained the 7 models, which I had studied about in the previous research. They had used 7 models. So I wanted to do it on the 7 models also, not a single one. Then what I chose is it was tree based, course tree. It was neural network based. Also, I used logistic regression, and there were other 5 also. So then 4 other also. So what we did after that, we calculated the accuracy, precision, recall, all these matrices or the parameters on which we can analyze how our model is actually performing. Then what I did is I converted them into joblib files, and on converting them into joblib files, I stored them and later used them for making an explainable AI model. because I don't want the machine learning part to be just interpreting like this feature is responsible mostly for like this model gives me this percent accuracy for interpreting the stroke patients. But what is the reason behind it? The explainable AI behind it. So we analyze this thing also. Then tools and technologies use simply Python, that is in Kaggle notebook I worked this time. Then we had the data handling part. In data handling, we had converted lots of data frames, dictionaries, 1D vector also, so that they were time series based. Because in my file, I was given the data in the form of sheets, and each sheet was one subject like that. Then we had the training and validation part. I used 10 cross-port validation also. I kept in mind to prevent any kind of data leakage, which I will talk later on. Then we have explainable AI. I use SHAP model as well as Lime model. Uh, I have done SHAP in full depth, but I used Lime just to check if my SHAP is right. So it was just to validate the thing I've already done. After that, finally, I made a visualization, or you can say I have a whole dashboard also to show you. We'll get to it. Next is the data set part. So I have already told you that this data set has 138 healthy patients or healthy person and 50 stroke patients. But I extracted only the angles from it because I was working on kinematic data. And also after that, I cleaned this data to prevent any kind of leakage, also summed them and checked if anything is infinity because it's not interpreted by a machine learning model. So I just excluded it. No, I had converted into NAN, then taken the average. And if it was totally infinite or something like that was not useful, then I discarded it, otherwise not. Then 50 is to 50 is the class balance I took. Okay. So there was a bit difficulty in extracting this data because I remember that in Python, I had loaded this file and first one was a README that was not needed in machine learning part. So I just continued it, means skipped or excluded in Python. After that, I had taken each subject one by one and taken it in full depth. I had analyzed each and everything. Then I moved on to the next thing, that is machine learning. After doing the machine learning, these are my results, you can see. So the best
So the
accuracies
best
were given by
accuracy was
logistic.
given by logistic regression, cubic SVM, and medium NN. So we just cannot choose any one of them because all of them are equally useful. But if we want to select one, then we can go towards AUC, that is the class separability. Then for the class separability, we can see backed trees work very well. It has the highest value for it.
Before this part, I want to show you the data sets. Oh, sorry, the codes I had done. So first one was I included all the files I needed. Then I imported all the necessary libraries. Then I loaded the kinematic data, made sure to skip the README files, and then convert it into a dictionary. Then I check for the sum, if there is any null values or something like that. Then I convert it into approximate entropy, sample entropy, fuzzy, and spectral. So I need to tell you one thing. For approximate and sample entropy, there were direct functions given in some library that was named antropy, ANTROPY. So I had taken it from there. And for the fuzzy one, I had written the logic that was given to me by as a proof in a research paper. And the last one is SP entropy, yes, spectral entropy. So that one was having used a Welch formula that was already given in ScineLab. No, Scikit-learn. Yes. So I had used that one also. So this is how I calculated all the entropy values for each subject. And after doing all these things, I tried to plot it just to see how the things are moving. You can see the deviation, like ankle of a stroke person. It is not going down here. There's a huge difference between this dependence. Again, you can see all these differences which lie here. So that was just a visual part, so that I get to know what is actually happening, not just the numbers that I need to read. So I included this visualization, and after that I trained all my models. Yes, I had loaded the models. Then MRMR is performed. Selected the top 10. Yes, and then I ran this evaluation. I got these results which I already shown you. So these were the final results. And also these were some of the plots I generated just to understand, which were later used in my results, which you can all find in the final one research paper I had written. For now, I will be submitting a report of 4 pages, but apart from that, in my GitHub, I have also added my report, which is about 10 pages. So this was all the research that I did in NIT Silchar. Okay. And then we moved to the explainable AI part. What we did here, let me show you. So firstly, I tried to use this SHAP model on all the features I had, like for ankle, pelvis, hip, knee. For all these things, I had approximate entropy, sample entropy, fuzzy entropy, and spectral entropy. But one thing was really different over here. That is, I cannot give these results to any scientist or a doctor to use. I need to convert them to original features only, that is, the angles that I was already given in the original features. So I needed to do this thing. I did a bit research. I got to know that if I firstly calculate the SHAP values for all the entropies, I can later sum them on because they have an additive property and I can revert back to my original features. That is the thing I did over here. So this is how my SHAP results look like after summing. This is for pelvis. It played the most important role in most of the all the seven. I think there was only one model in which hip was on the top. Otherwise, in every one, it is pelvis. Then we have hip, then ankle and knee. Yes, I must tell you that the knee angle almost didn't play any role in any of the machine learning part. If we do not have it, even then we can make the results. So it was mainly dependent on the pelvis and hip. And also you can see over here, this line also has almost the same results as that of the SHAP model. This was how I actually validated that, yes, I have done the right thing. You can see here that in case of pelvis and hip, yes, for the pelvis, it's red over here, and for the hip part, it is always blue over here. So it means that lesser is the movement in hip, more is the healthy the person, but lesser is the movement in pelvis. If the pelvis is stiff, then that person is a stroke person. So red means stroke, blue means healthy. And similarly, I had shown the result for all the seven SHAP models. Here you can see there is pelvis, pelvis, pelvis. Only hip is present in cubic SVM part. That were the interpretations given by our model. Now, before moving on to the interactive dashboard, let me take you back to the another code file that I have for the final XAI. So I again loaded all these things. Okay. After that, I again loaded these job lib files and the trajectories that I had. And what I did later on, I just checked their accuracy once again, if they are doing perfectly well or not. Then these SHAP values and the base values, which are averaged, they were calculated. And based on all these things, I was able to make these graphs. I was able to interpret whether I'm doing these things right or wrong. So these were the individual parts. These were the waterfall graphs you can see. For the hip, it is blue. For the pelvis, it is red. So that is again the same explanation I want to give, that if pelvis is stiff, the person is a stroke person. But if the hip is stiff, then it's a healthy person. Means lot of movement in hip means stroke person. Like that. Then I interpreted the same thing. I've also generated line for individual machine learning models and also for combined. These were nearly the same as that of my SHAP models, which gave me a good idea. Yes, I have done the right thing. So that was how I've done it. And I've saved everything to be used later on. Then I want to take you to that interactive dashboard. Yes. So for the dashboard, I have built a dashboard that is in SignLab. It is an open source, just like MATLAB file. So you can see I have trained these models and the SHAP explainable AI. So I have made 3D boxes, something like that. And then I had given one trajectory for the healthy person and one for the stroke person. This is just for a visualization purpose that we better get to understand what is actually happening. So what my model does is it has a red and blue dot, the four angles. Okay. I had adjusted the lengths, giving femur bone or the thigh the most length, then leg, then ankle, and then your feet, like that. I have given all the seven models in its backend. So that is how it's building the logic and showing me the SHAP values, moving a whole gait cycle 0% to 100% for both the stroke and healthy patient. And apart from that, there are 4 graphs. Let me show you how it's actually working. Yes, this one it is. Okay, so firstly, I have to select any model. For example, I'm selecting logistic regression. You can see that its accuracy is 92.3%. The main XAI driver is pelvis. And also you can see how many red and blue dots. And you can see pelvis is the main culprit here. So for the pelvis part, you can see that here, knee. We have to select a model, for example, logistic. Then you can see we have selected pelvis is the main culprit. Then we can see the stroke pattern. Pelvis is the main driver. And for the stroke pattern, you can see knee is the most stiff one. It has 829 red and only 176 blue. So how it's working, whenever the leg will be moving over here and there in both these boxes, you will see that this black line stands for the stroke patient, blue one is for the healthy patient. Similarly, you will be able to see the dot moving across it from 0 to 100 on x-axis like that, and you will be able to interpret that how it is actually working by the color of dot, because it will be changing dynamically. Let me show you. When I play it, you can see how it is actually working. How I made it possible? I had given the trajectories in backend, the SHAP values, the machine learning models, and apart from that, I also used this trajectory or color changing. This thing was done by using simple standard deviation. What I kept in mind, like there is a deviation for healthy person. Yes, healthy person doesn't always move the same way always. So there's a bit difference in their walking. That doesn't matter. That is just the deviation. But if it crosses the deviation higher or lower, a lot difference is present, then the dot will turn red, otherwise it will stay blue. That is how it's happening. You can select any model and use this and get to know. And if you decrease this, you are decreasing the multiplier. It means sensitivity. Actually, I calculated the sensitivity. It came out to be 0.76, which I have provided in its code. But for now, it has 0.76, but now I'm decreasing it. So it may be able to show that there's mild deviation like that could also be shown. So you can see the movement, only mild deviation like that. And I also included this audio part. If a person wants to use this dashboard and no one is there to tell you how to use it, then this audio will give you the instructions like that.
Welcome to the Kinematics Gait Sim XAI Stroke versus Healthy Gait Simulator. This dashboard allows you to analyze and compare healthy and post-stroke gait kinematics in real time.
Like that. It's a full audio. I had played just a bit. So then let's move back. Let's wrap up. So what we got to know, kinematics only can also interpret really well. It has an accuracy of 92.3 at most. And also the AUC score is mostly 0.95 always. Okay. Then we use SHAP and Lime model to prevent the black box things. We wanted to show them that yes, the things that we interpreted really actually hold value. They are proven. So we did that part also. And the limitation was that we had a bit less data, and also EMG was excluded as of now, because I told you apart from that we can also do this analysis, but that could also be included only when if we have accurate data, because I never wanted to add any kind of noise or bad data to my work. So I excluded it for now. And also there is only a certain age gap present, but if you want to know before it or after it, something like that, it you may need to add that data also. Then continuous interpretation, yes, it could be made in future, that we could use not just for classification, we can convert it into FAC score that tells whether a person is dependent on someone or can walk independently, or how much stroke has affected them like that, and their gait speed. That could also be analyzed, but for that again sensors are needed. Then neuromuscular mapping could also be done for the EMG signals, and broader validation things could also be made. So that was all the thing. And one thing to keep in mind, that knee was not an XAI driver in the whole thing. Yes. So that was the whole project I had worked on. It had taken about 6 months at NIT Silchar, and I'd really like to thanks all my teachers from IIT Guwahati and NIT Silchar, all the mentors. They were really well and helped me throughout. Thank you so much.